A team of scientists pulled up a batch of images they never expected to be looking at, sent back from a spacecraft that was never built to take them. It was supposed to be studying the sun. Instead, sitting in the data was something that had no business being there. A faint, glowing outline of continents, plateaus, and lowland plains, visible in ordinary light, the kind of light your own eyes can see, on a planet that has kept its surface hidden behind an unbroken shroud of cloud for the entire history of human observation. Nobody on the mission team had planned for this. The camera wasn't designed for it. There was no proposal written, no years of instrument design, specifically aimed at solving this exact problem, the way there had been for every other spacecraft that had ever tried and failed to see straight through Venus's clouds using ordinary light. And yet there it was, the ghost of an entire planet's geography, glowing faintly through nearly 40 miles of solid cloud cover, captured by an instrument built to watch the sun's outer atmosphere, not the surface of the second planet from it. This is the true story of how NASA accidentally captured Venus like it had never been seen before, and why the scientists involved are still, years later, calling it one of the strangest surprises the mission has ever produced. To understand why this discovery is such a strange one, you first need to understand what Venus actually looks like from the outside, and why its surface has remained essentially invisible to ordinary observation since the invention of the telescope. Venus is often called Earth's twin, and in terms of raw size and mass, the comparison holds up reasonably well. But the similarities stop almost immediately after that. The entire planet is wrapped in a permanent, unbroken layer of thick cloud made largely of sulfur dioxide and sulfuric acid, dense enough that no telescope on Earth, however powerful, has ever been able to see straight through it to the ground below using ordinary visible light. Peer at Venus through even the best optical telescope ever built, and all you will ever see is a smooth, featureless, pale yellow ball, a planet that keeps its actual geography a complete secret from anyone trying to look at it directly. For decades, that meant scientists had to get creative if they wanted to know anything about what was actually happening beneath those clouds. In the early 1970s, the Soviet Union's Venera landers became the only spacecraft to ever physically touch down on the Venusian surface and transmit images back before the planet's crushing atmospheric pressure, roughly 90 times. That of Earth's and blistering heat destroyed them, typically within about an hour or two of landing, their camera lenses and electronics slowly cooking under conditions closer to the inside of an industrial furnace than anything resembling a typical planetary surface. Those images showed a genuinely alien landscape up close, flat volcanic rock stretching to the horizon under an oppressive orange sky, but they only ever captured tiny individual patches of ground from wherever each lander happened to touch down. Nothing resembling a global picture, and no lander survived long enough to ever look up and see anything beyond the small patch of rock immediately in front of it. In the 1990s, NASA's Magellan mission solved the global mapping problem a different way entirely, using radar instead of ordinary light, bouncing microwave signals off the surface from orbit, and reconstructing a detailed map of the planet's terrain from the echoes that bounced back. Radar doesn't care about clouds, so Magellan was able to build the first genuinely global map of Venus's surface, revealing volcanic plains, highland regions, and evidence of relatively young, possibly still active geology. Japan's Akatsuki spacecraft later added another piece to the picture, using infrared wavelengths capable of slipping through gaps in the clouds to study Venus's atmospheric circulation from orbit. But none of these methods, radar, infrared, or the brief handful of surface-level snapshots from the Venera landers, had ever produced anything resembling a direct, visible light view of the planet's actual surface features from space, the same basic kind of image you'd get by simply pointing an ordinary camera at the ground and letting light do what light normally does. That's what makes the story of NASA's Parker Solar Probe so unexpected, because Parker was never designed to solve this particular problem at all. Launched in August of 2018, Parker Solar Probe exists for one overriding purpose: to fly closer to the sun than any human-made object in history, diving repeatedly through the sun's outer atmosphere, the corona, to directly measure the solar wind and help scientists finally understand some of the most persistent mysteries in solar physics. Questions like why the corona is dramatically hotter than the sun's own visible surface sitting just beneath it, a genuine decades-old puzzle that has nothing whatsoever to do with Venus. The spacecraft is protected by a thick, heat-resistant shield capable of withstanding temperatures nearing 2,500 degrees Fahrenheit on its sun-facing side, while the instruments, tucked safely behind that shield, operate at something close to room temperature, an engineering feat that took the better part of 6 decades to become technically achievable after NASA first began seriously considering a mission like this back in the 1950s. To achieve those repeated, close solar passes, Parker relies on a clever engineering trick: a series of gravity-assist flybys of Venus, using the planet's gravity to gradually tighten and reshape its orbit around the sun with each pass, bleeding off orbital energy a little at a time without needing to carry the enormous amount of fuel that kind of orbital adjustment would otherwise require. Venus, in other words, was never Parker's actual destination. It was a stepping stone, a periodic detour on the way to the spacecraft's real target, the Sun itself, visited again and again purely as a means to an entirely different end. Parker does carry a camera, called the Wide Field Imager for Parker Solar Probe, or WSPR for short, but that instrument was built with an entirely different job in mind. WSPR exists to study faint structures in the solar wind and the Sun's outer corona as Parker makes its close approaches, watching for the kind of subtle streams and eruptions of solar material that are otherwise extraordinarily difficult to observe. When mission scientists realized Parker's trajectory would carry it past Venus's night side during a flyby in July of 2020, they had a modest, practical idea. Point WSPR at Venus's clouds during the pass and use the images to measure how fast those clouds were moving, treating the flyby as a convenient bonus opportunity to gather a small, useful piece of atmospheric data along the way. As Angelos Fourlides, the WSPR project scientist at Johns Hopkins University's Applied Physics Laboratory, later put it, the actual objective was simply to measure the speed of the clouds. Nobody was expecting anything more dramatic than that. What came back instead stopped the team in their tracks. Instead of showing just the featureless tops of Venus's clouds, the WSPR images appeared to show straight through them, revealing a faint glow with visible structure, patterns that looked unmistakably like continental regions, plains, and elevated plateaus on the actual solid surface of the planet. Sitting nearly 30 miles beneath the clouds, the camera was technically pointed at. It made no obvious sense at first. WSPR wasn't designed as a surface imaging instrument, and visible light, by every existing understanding of Venus's atmosphere, simply wasn't supposed to make it down to the ground and back up through that much cloud cover intact. Sulfuric acid droplets and sulfur dioxide haze are exactly the kind of dense, light-scattering material that ordinarily swallows visible light whole. The reason nobody had ever managed to pull off exactly this kind of image before, despite decades of dedicated missions specifically trying. And yet there it was in the data, unmistakable enough that the scientists involved knew immediately they needed to look again, more carefully, the next time Parker made a similar pass, rather than simply filing the anomaly away as an instrument quirk or a processing artifact and moving on to the mission's actual priorities. That second chance came on February 20th, 2021, during Parker's fourth flyby of Venus. This time, the spacecraft's orbital geometry lined up almost perfectly, allowing WSPR to capture the entire night side of the planet in one continuous pass rather than just a partial glimpse. Brian Wood, an astrophysicist at the Naval Research Laboratory and lead author of the eventual study, described his own reaction to seeing the results in blunt, unscientific terms. The images and video, he said, simply blew him away. The team stitched the individual WSPR frames together into a short video, and what it revealed was the ghostly, glowing outline of an entire planet's geography, rendered visible for the first time ever in ordinary visible light, from space features, including the massive highland region known as Aphrodite Terra, the Tellus Regio Plateau, and the sprawling lowland plains of Aino Planitia, all faintly traceable through clouds that had hidden them from this kind of direct optical view for the entire history of astronomy. Here's the physics that eventually explained what the team was actually seeing, and it turns out to be a genuinely elegant quirk of light and heat working together in an unexpected way. Venus's surface, thanks to a runaway greenhouse effect driven by its thick carbon dioxide atmosphere, sits at a scorching, remarkably uniform temperature of roughly 860 degrees Fahrenheit, hot enough to melt lead, and hot enough on its own to make the solid ground glow faintly. The same basic principle that makes a metal poker glow dull red once it gets hot enough in a fire, or the way the heating element on an electric stove begins to visibly glow once it reaches a certain temperature. That glow radiates outward from the surface across a range of wavelengths, and it turns out that the very longest wavelengths of visible light, right at the border where visible light shades into the near-infrared, are just barely able to slip through gaps and thin spots in Venus's dense cloud cover, rather than being completely absorbed and scattered the way shorter wavelengths are, essentially threading a needle through the one narrow window in the planet's atmospheric chemistry where enough of that radiated heat manages to escape intact. During the day, the faint red glow gets completely overwhelmed by the far brighter sunlight bouncing directly off the tops of Venus's clouds, drowning out any hope of seeing it the same way you'd never notice a dim, glow-in-the-dark sticker sitting out in full daylight. But on the planet's night side, with all that reflected sunlight removed from the equation, WSPR's sensitive imager was able to pick up the surface's own faint thermal glow directly, essentially photographing Venus's own heat leaking out through gaps in its own atmosphere, rather than photographing reflected light bouncing off anything at all. Cooler, higher elevation regions on the surface, like the highlands of Aphrodite Terra, glow slightly less brightly than the lower, warmer plains surrounding them, since higher altitude terrain on Venus runs somewhere around 85 degrees Fahrenheit cooler than the lowlands below. A genuinely enormous difference in temperature by everyday standards. though a comparatively subtle one against a backdrop already sitting at 860 degrees. That temperature difference was exactly enough to make elevated terrain show up as darker patches against the brighter glow of the surrounding lowland plains and Whispers images, giving the resulting pictures real topographic contrast. Essentially, a crude but genuine visible light relief map of the Venusian surface, built entirely from an instrument that was never supposed to be capable of producing one. Researchers were able to cross-reference these darker and brighter regions directly against Magellan's decades-old radar elevation data. And the match held up convincingly. The exact highland regions Magellan had already mapped by radar showing up as measurably dimmer patches in Parker's visible light images, a genuine independent confirmation that Whisper really was picking up authentic surface temperature variation, not some kind of coincidental artifact or processing error. The team's full analysis of both flybys, the accidental first glimpse in 2020 and the deliberate, complete nightside pass in 2021, was formally published on February 9, 2022, in the journal Geophysical Research Letters. Alongside the surface features themselves, the Whisper images also captured something else nobody had specifically been looking for. A faint, luminescent halo of oxygen glowing in Venus's upper atmosphere, an atmospheric night glow phenomenon that had previously only been studied through separate spectroscopic instruments aboard other missions like the European Space Agency's Venus Express, now visible instead as a genuine, direct visual feature wrapped around the edge of the planet in Parker's own images. It's worth pausing here to appreciate just how unusual it is for a mission's most striking discovery to arrive completely sideways from its original purpose. Parker Solar Probe's entire multi-billion-dollar mission architecture, every instrument bolted to its frame, every ounce of its heat shield, exists to study the sun. Venus was never meant to be more than a gravitational stepping stone, a brief, useful detour on the way to somewhere else entirely. And yet, almost by accident, using a camera built to watch faint structures in the solar wind, Parker managed to produce something no purpose-built Venus mission had ever achieved before it. A genuine, direct, visible light view of the planet's actual surface geography from space, a feat that had eluded dedicated Venus orbiters and landers for the better part of a century. That accidental success didn't stop with the surface itself, either. During these same flybys, Parker's other instruments picked up additional details about the Venusian environment that added further texture to the picture. WSPIR also captured images of Venus's orbital dust ring, a faint, donut-shaped band of microscopic particles trailing along the planet's orbital path around the Sun, left behind by countless small collisions and gradual erosion over cosmic timescales. A separate instrument aboard Parker called FIELDS took direct measurements of radio wave activity in Venus's upper atmosphere, data that has since helped researchers understand how that atmosphere shifts and changes across the Sun's roughly 11-year cycle of rising and falling activity. And in a study published in December of 2021, researchers using Parker's data rediscovered and mapped what's known as Venus's tail ray, a comet-like stream of charged particles trailing behind the planet, stretching outward for nearly 5,000 miles, shaped by the same solar wind that Parker's entire mission exists to study in the first place. So why does any of this actually matter, beyond the simple, undeniable coolness of accidentally photographing an entire planet's surface with the wrong camera? Because Venus, for all its hostility today, is increasingly understood by planetary scientists as a genuinely crucial piece of the puzzle for understanding how rocky planets evolve over billions of years, and specifically, how a planet that may have started out relatively similar to early Earth can end up somewhere as different and inhospitable as Venus is now. Some researchers believe Venus may have once had liquid water on its surface, potentially even oceans, before a runaway greenhouse effect took hold and transformed it into the crushing, furnace-hot world it is today. A slow-motion planetary catastrophe playing out over hundreds of millions or billions of years, rather than any single dramatic event. Understanding exactly when that transformation happened, how quickly it unfolded, and whether it was driven primarily by the sun's own gradual brightening over time, or by something more specific to Venus's own internal geology, remains one of the genuinely open questions in planetary science, one with implications that reach well beyond Venus itself. Every additional piece of surface data, even data captured almost by accident from a mission built for an entirely different purpose, adds another data point to that larger question, one with genuine relevance to understanding the long-term habitability, or eventual loss of habitability, of rocky planets in general, including, implicitly, our own. That growing scientific interest in Venus isn't limited to second-hand data gathered incidentally along the way to somewhere else, either. NASA has 2 dedicated Venus missions currently in development specifically to build on exactly this kind of momentum. Da Vinci is designed to send a descent probe directly through Venus's atmosphere down toward the surface, measuring the chemical composition of the atmosphere layer by layer along the way, gathering exactly the kind of detailed in situ chemistry data that no orbiting camera, however clever its accidental discoveries, could ever hope to capture from a distance. Veritas is designed to orbit the planet and produce a new, dramatically higher resolution radar map of the surface than anything Magellan achieved back in the 1990s, potentially revealing whether some of Venus's volcanic terrain is still geologically active today, a question that remains genuinely unresolved and that could reshape how scientists think about rocky planet interiors more broadly if the answer turns out to be yes. Between them, and building on the same broad wave of renewed scientific interest that Parker's accidental images helped fuel, Venus is quietly shifting back into serious focus. After decades spent playing second fiddle to Mars in the public imagination, treated less like a dead, hostile dead end and more like an essential cautionary case study in what can happen to a planet that starts out looking a lot like home. Here's what's genuinely worth sitting with once you strip away the technical detail. A spacecraft built entirely to study our own star, using a camera specifically designed to watch faint wisps of solar wind, ended up producing the first true visible light view of an entire planet's surface geography from space, a feat that had eluded every purpose-built Venus mission before it, purely because a research team decided to point an unrelated instrument at a familiar planet during a routine gravity assist flyby and simply see what happened. Sometimes the most striking discoveries in space exploration don't come from missions specifically engineered to find them. They come from scientists paying close enough attention to notice when their instruments are quietly doing something nobody asked them to do, and having the curiosity to look twice instead of moving on. If stories like this are what you come here for, hit subscribe, turn on notifications, and let me know in the comments what you think Parker Solar Probe, or any other mission currently flying, might accidentally stumble onto next, because judging by this particular surprise, some of the biggest discoveries in space exploration are still happening completely by accident.